Okay, this is back for week 2, and this week we're going to look at slightly soluble salts. All right, so if we go way back, I think it was chapter 4, and we had a list of solubility rules. And those solubility rules told us what things were going to be soluble in water and what salts were not. So we either said soluble or insoluble. Well, it turns out that even those things that are insoluble are soluble just a little bit. So if we were to look at something like AgCl, which we said was not soluble, it turns out a little bit of it dissolves in water. So we would form the 2 ions, silver and chloride. Now if we wanted to look at the equilibrium expression, this would be Ag plus times Cl minus. And I would not include the AgCl solid because solids don't show up in my equilibrium expression. Now we had Ka for acids, we had Kb for bases, and now we have a new one, and it's called the solubility product constant. So it's Ksp, and that's what we use for slightly soluble salts. So what we're going to do now is go and take a look at a couple problems that we could do using Ksps. All right, so the first one says that the molar solubility of CaF2 is 1.24 times 10 to the minus 3 molar. Now that's pretty small because it's to the -3. That's telling me how much of that would dissolve. So the first thing I'm going to do is write my equation. All right, and I have 2 F's, so I'm going to put 2 F's over here. Now they've given me the solubility already for this, so I'll write it here. And since this is 1:1, I would have the same amount here. And this has a 2, so that means this is going to be twice as much. So now I'm going to write my Ksp expression. So this is going to be Ca times the concentration of my F minus squared, since there's a 2 out in front. So if I want to calculate Ksp, I'm just going to plug in those solubilities. So 1.24 times 10 to the minus 3rd, and my other one's 2.48 times 10 to the minus 3rd, and that's going to be squared. So I'll plug that into my calculator. And I got a Ksp of 7.6263 times 10 to the -9th. And there is no label because it's just telling me my equilibrium constant. Okay, so if you are given a molar solubility, you can find Ksp. So this is solubility to Ksp. All right, we're going to do another example. This time we're going to go backwards, and we're going to go from our Ksp in order to find our solubility. Okay, so this time we are going to look at BaIO3. So, as always, I'm going to write my equation. And this time they have given me the Ksp. I'll write it over here. And this is 6.0 times 10 to the minus 10th. All right, since I was not given the molar solubility, I'm going to say that it's X. This would be X, and there's 2 of these, so this would be 2X. And then I need to write my equilibrium expression. So it's going to be BA times IO3 squared. I know my Ksp, 6.0 times 10 to the negative 10th. I know my BA was X, and we said my IO3 is 2X, and this is supposed to be squared. So 6.0 times 10 to the minus 10th is equal to, so 2x squared would be 4x squared, times another x is 4x cubed. So I'm going to take 6 to the negative 10th divided by 4, and then I'm going to do the cubed root. So I'm taking it to the 1/3 power. And I got 5.3 times 10 to the negative 4th molar. Okay, and that's telling me X, which is the molar solubility of the BaIO3. So that's how you can go from solubility to Ksp and back and forth. And in our next lecture, we'll look at adding a common ion.